Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, if you're joining us and you have any questions, if you're on Zoom, just look at the top of the bottom of your screen, wherever your Zoom controls are, find that Q&A button, click on that. It'll open a new box for you. You can type in your question, hit submit, and I'll get to those questions at the end of the session. If you're joining us live on YouTube, just feel free to use that live chat function wherever it happens to be on your screen. And by doing it that way, you just ask your question, and I'll get to those at the end of the session as well. So my name is Jason Gabrinas. I'm one of Snap-on's National Diagnostic Technical Trainers. Been in the training department the last 8 years or so, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Then before I did that, it was a couple years as a diagnostic sales rep with Snap-on. So I had 30 different Snap-on franchisees that I worked with, as well as the shops that they serviced, to help everyone get the most out of their diagnostic needs. Then before I did that, I was a tech at a Subaru dealership, or should I say became a diagnostic tech, I guess, in my time there. And, I always seemed to end up with those drivability problems, the weird wiring problems, those intermittent problems that would show up. Those would always seem to end up in my bay. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bay. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So all new topic today. We are sticking with our component testing subject. And today we're talking cam and crank sensors. So cam and crank sensors going along and helps the computer know where is that engine in its rotation, what cylinder is in top dead center, and so on and so forth. There are 4 different types that we're going to focus on here, and this should cover pretty much all of them. We have a magnetic pulse generator type. We have a Hall effect switch, which there's a couple different ways we can use that Hall effect switch, and we'll talk about that. Optical sensors. So those are probably the least common out of the ones we're going to talk about. They weren't used very often. And then also the Magneto-Resistive sensors, which seem to be maybe getting a little more popular nowadays as well. So the first one we want to talk about is that magnetic pulse generator. So this is a fairly simple unit, and I'll tell you, all but 3 out of the 4 of these types of cam and crank sensors really work on that electromagnetism that tons of things on the car seem to work on. So you can see this is a cross section of a magnetic pulse generator sensor. It's just 2-wire sensor, terminals right there, goes in, and we have our core in here. It's usually an iron core. Then we have a magnet at the end, and then around the core at the bottom we have our coil of wire, right? So we have usually it's copper wire spun in a coil. And when we pass metal through this and we have our magnetic core, well, then we generate electricity. These actually generate their own voltage. They don't need to be supplied a voltage supply. They just generate their own electricity as they go. So here's just on this sample car that we're talking about, we see the crank sprocket right here, and built into the crank sprocket are these little nubs on the ends. And when those nubs go by this electromagnet, it will generate an electronic voltage, goes out to the PCM. And this one also is in an AC type waveform. So we have, it goes above 0 and below 0 as well. So it'll generate us a pattern that'll blip every time one of these little teeth go by. And once again, it is an AC type waveform. So induced AC voltage output. We can see a sample scope capture on the right hand side here. This red dotted line is where 0 is. We can see it goes above a little over 10 volts, goes below a little below negative 10 volts. So that's our swing right there. Depends on the vehicle, but voltage output is relative to the engine RPM. So the faster it is spinning, the higher the voltage will be. So the voltage goes up the faster we spin. And of course, the frequency gets closer together too, because it's spinning faster, right? So those marks are coming by a lot faster than they would be at an idle. So those will go in a lot closer together like that. Now, coil winding, the polarity of the coil winding is specific for that vehicle or for that system. You don't want to reverse the leads. If you ever replace a connector or something like that and you got a D-pin, make sure you put the pins back in the right spot. Also could cause an issue with aftermarket I've seen too, where they put the pins in the wrong way, just because that's aftermarket parts sometimes, right? So that could cause an issue as well. And that is a 2-wire sensor. Also note on this just popped into my head too. From year to year, could have a change in the way that this works. So I give you an example. Pre 2004 on a Subaru, generally speaking, on the 2.5 engine, it would look like this. We'd have just six of those little teeth there. Now, starting in 2004, some of them went to a 36 tooth configuration where it's got 36 teeth 10 degrees apart, and that won't work on the vehicle that has just the 6 teeth. So you got to make sure, because you could get a used engine, it would bolt right into the car, but it wouldn't start up because it wouldn't work with the computer. The computer is expecting a certain signal, and if it doesn't get that signal, I've seen that a few times happen, actually. That just popped in my head there, where if it's expecting a 6 signal, it's getting a 36 signal, that's a problem, right? So we got to be aware of polarity. We also got to be wary of what signal am I sending the computer. We want to make sure they match if we're swapping an engine or something of that nature. So just that could cause a no start issue, that could cause a drivability issue. So we want to make sure that we're aware of that. Now, the waveform, as far as how the waveform should look, just very similar to how we have it on the screen right here. We have an up and a down, just a simple analog sine wave on both sides. We can see how we got a little flat spot here because they're grouped together in threes. So we can see the 3, the 3, the 3. And there's a little bit of a gap right there as well. So we can just see how they're grouped together. That's how it should look on that car. Next one we have is a Hall effect switch. So there's 2 different types that we're going to talk about here. This is probably I guess we'd call it the older style here. Either way, though, it is a toggling DC voltage output. So you should see a square wave pattern on the screen when you're reading it. In this case, unlike the signal generator, the voltage generator, the signal is not RPM sensitive, and it is stable at a very low speed. So the voltage will not change with RPM. The frequency will still change. It will get closer together the faster the engine goes, but the amplitude of the signal will not change. Commonly a 3-wire sensor needing voltage, feed, and ground to operate. So you have power, ground, and a signal wire. Some vehicles will have a dual unit and have 4 wires and 2 output signals on a distributor type. Now, if we look at the top here, we have these, looks like kind of the top of a castle or something like that. They call those a shutter blades. So our Hall effect switch over here, we have a magnet and a sensor, and in between that, there's a gap. So going in between that gap as it spins is going to be these shutter blades. When those shutter blades go through that gap and cover it up, so to speak. So we're going to have an open spot and then we have a closed spot. When it's closed, that will generate that signal and that Hall effect sensor, and that will send out the signal to the vehicle. Now, we had a vehicle that we looked at that the customer suspected that it was a crank sensor problem. The vehicle would run for a while and then it would stall, and it would seem to have no rhyme or reason. It could be hot, could be cold, could be running for 10 minutes, could be running for 2 minutes, 30 seconds, whatever. It would just stall, seemingly on its own. So they suspected maybe it could be the crank position sensor on this vehicle. So it was a Ford pickup with a 351. And on that, it had a ignition control module on the distributor on that, in that case. So here is, if we wanted to test that ignition control module, which is where we're going to look at the signal. We have a crank position sensor, which is built in. It looks kind of like those blades that we saw there. And then there's also a spout. So that's spark out of the PCM on this vehicle. So the control module will read the crank signal, sends it to the ECM. The ECM then sends out the spout signal that controls when the spark happens. And then the ignition coil negative is what actually sends the signal to the coil in order to make sure it is firing when it needs to. And then, of course, power and ground. So what we wanted to do is we wanted to check, well, is it the crank sensor, or is it the ignition, or is it the computer? Right. So if we think about how we have this set up here, we have the crank position sensor, which is the signal that gets sent out to the computer. Then we have the ignition control. So that is actually connected to the coil, telling the coil when to fire. And then we have the spout, which is coming back from the computer into the ignition. So we have our crank going out, spout coming back in, which tells the ignition when to fire. So we were recording it, had it all hooked up like this, recording it, seeing when is it going to fail. And when it does fail, who's going to fall out first. Now, you also notice that crank position sensor, it is a Hall effect sensor, and it goes a little bit over 12 volts. So it should be Should be about alternator voltage when it's running. Oh, another thing with Hall effect sensors that brings to mind is we want to make sure that it is toggling through its entire voltage range. So if it's supposed to be a 12-volt signal, we want to make sure we see at least 12 volts in there, because the computer really only cares if the signal gets to a certain point above a certain threshold. So if this was outputting 8 volts and it's supposed to be 12, the computer would have no idea what's going on, would just say the signal is missing. So just keep that in mind as well. Hall effect sensors got to switch through the whole range of motion, certain times, certain conditions that might, or certain failures that might be a problem. So anyways, on this truck, we have the crank signal going to the computer, we have the spout signal coming back, and then we have the ignition coming out of the ignition module, as we said. So recording went for a couple minutes. Finally, the truck did stall, which was kind of lucky. It's nice that it happened to happen when we were there hooked up. So when it did stall, though, we stopped the recording. We zoomed out because we wanted to see, well, who fell apart first. So if we look, remember, that's the crank signal, that's the coil, and that is the spout signal. So let's zoom back in a little bit and see who fell out first. Now, being able to use a scope in this way, being able to compare multiple signals over a period of time, well, I can see crank sensor is not my issue, is it? Because my crank sensor continued on even after the spark stopped. So this is where I was firing the coil right here, and that stopped. And then the vehicle continued to run. Now see how also these signals are getting further and further and further apart. Now, why is that? Because that's when the truck stalled, right? So the engine's spinning slower and slower, and then it finally stopped. And then the spout signal would be similar to, it should follow along pretty close to how that crank signal went, right? So we can see from here to here that the coil fell out before the crank stopped, and the only reason the crank signal stops because it stalled, and it was almost 600 milliseconds, so a little over half a second it took for it to lose ignition before it actually finally died. So that's not a long amount of time. That's like 2 blinks of your eye, right? It's a half a second. But being able to see that on a scope and pick up on that, we can say, well, that crank sensor is not the problem in this case. It was a bad ignition control module, right? We get heat, vibration, any of those things could cause that issue, but it wasn't the crank sensor. And by testing it in this way, we were able to see that. There's another way that Hall effect sensors operate as well. So this is on a newer vehicle, not distributor, but it still uses a Hall effect sensor. Many vehicles still use Hall effect sensors just because they're pretty reliable. So we have the cam sensor here, goes into the mounting box. Here is a cross section of that. So we have, of course, the electromagnet in there. We have the windings in there. And in this case, on a Hall switch, what they do, instead of having the shutter go through the gap, we remove material on the little plate that it's reading. So when the magnetic field that's generated, now this is a 2D, I'm not the best artist in the world, right? So that's my approximation of a magnetic field, right? We know it's in 3D and makes different shapes. But anyways, when that magnetic field is not being crossed by my metal plate, it outputs a signal. So as we put this in motion, we see it turning. In this case, when we take the metal away and we take that out of the magnetic field, is when it generates a signal. Now, some vehicles, depending on the manufacturer, sometimes it'll be a constant ground and then generate a voltage out, or it can be the other way. Maybe I have 5 volts in and it pulls it to ground. Could work either way. So you also want to research with the manufacturer how it's supposed to work. Does it pull up or does it pull down? Right, so we can see that, and that is just another Hall effect switch use, and in this case, it's a digital. Next one we have, probably the least common one, but they are still out there, and you may run into them, and you may need to test them. So let's talk about how they work. So it's an optical triggering device. So this would be known as GM's OptiSpark system. Nissan had a system like this, and I believe Honda did as well. I don't think anybody uses it anymore, but you may still find one coming to your shop, right? So once again, it is a toggling DC voltage output, so you're going to see a square wave. Nice thing about this also is a stable voltage output throughout the RPM range, so the voltage will stay the same. Frequency, of course, will get closer together the faster we go. Does require voltage and ground to operate, and most unit has 4 wires and 2 output signals. So I'll have power, ground, and then 2 signals. And how it works, if we look at the cross section here, there's a disc that rides on the distributor shaft, and we have LED lights. On the other opposite side of that disc are photosensors. And you'll notice with that disc, we have multiple holes cut in it. So on the outside, they call that the high resolution disc. It's going to have multiple cutouts evenly spaced all the way around, probably usually about the 60s range, because that's a good multiple of 360 degrees. And then we'll also have some smaller cutouts in there that will send a pattern to the computer. Here's an example on GM 350 where they had it. So they had the pickup assembly and the optical sensor there. And then here is a closer look at that setup. So we have the optical sensor here. So LEDs, when that light hits the photo sensor, it sends a signal. So in all the holes, the light will go through the holes, right? The light will go through the holes, hit the photo sensor, sends a signal out. So I have a high resolution signal on the outside, low resolution signal on the inside there. So high resolution signal is just going to be a constant square wave. And then you'll notice these different sized holes here will turn that signal on for longer or shorter. So if we were to look at a scope pattern output of that, see we have a long one, we have a really tiny one, we have a medium sized one, a really tiny one, a little bit bigger one, a couple different sizes. Depending on where these fall in order, will tell the computer what cylinder is where in the timing, right? In the firing order. So let's say that's 1 8 3 4 6 5 7 2, right? I think that's off the top of my head there. But whatever signal it is there, it's going to give it to the computer, and the computer knows when to fire it. And then we have magneto-resistive sensors. So magneto-resistive sensors are more recently being used, and they're using them for more than just cam and crank sensors. So the same principle applies here. Typically, it is a 3-wire sensor. You will see that digital 5-volt square wave out or 12-volt square wave, depending, just like a Hall effect switch. It is very sensitive to damage, the trigger wheel imperfections, if there are imperfections on the trigger wheel, and remember that. Will cause sensor noise and will cause issues. We'll talk about that in a second. In this case, the PCM does not supply the voltage either. On a magneto-resistive sensor, it pulls up 5 volts and then toggles down to ground. So if we look at how the sensor is set up, it has a 1 and a 2. So they're a little ways apart based on where this, what they call an encoder wheel. So encoder wheel is a bunch of permanent magnets stacked together. So I have north poles and south poles. As it spins by, we have another magnet here. So it's an electromagnet. So as it spins by, it will see, number 1 will see the signal before number 2 does a few milliseconds apart. That sends an analog output out, which gives a differential output to the computer, which then can be translated into a square wave. So when you're analyzing this with a scope, you'll see the square wave. Everything else happens internally inside the sensor. But just know it's a little bit different the way it works, because the wheel, or encoder wheel, as they say, is magnetized. So that is a spinning magnet. Good to know. They also use that for wheel speed sensors a lot now too. It's much more accurate with the way that it senses. So here's an example, and you may know of this example. So this is on a 3.6 liter Dodge, Chrysler, what have you, Pentastar motor. That uses a magneto-resistive cam position sensor. Now you can see how it's set up here. These are those 2 encoder wheels I was talking about. So these are magnets, permanent magnets that spin on the end of the camshaft. And then you'll see the cam sensor is able to read both when we have our sensor units right there. Now, remember what I said about magneto-resistive sensors. If we have a problem with the sensor wheel, contamination, other issues, that will cause a problem. So a very common problem with these as well. I got a camshaft that's made out of steel, probably, right? And I have roller rockers in this vehicle, in this engine as well, and those are steel, right? And then, well, steel on steel, over time it might wear out, right? Especially if you have an oiling problem in the vehicle. So if it wears out, where's that steel going to go? What's that steel going to look like to start? So it's going to get your little fine metal shavings inside. And where's that going to go? Because everything's bathed in oil, so it goes into your oil. And then if it's in the oil, it's also going to be bathing the camshaft, yes? And then what's on the end of the camshaft is 2 spinning magnets. So all the metal that's in that oil is going to get picked up by these magnets, and then they're now contaminated, and those cam sensors won't work, or they'll throw codes. You will have some sort of an issue with this. This is very common on these engines. So you may get a code for a cam sensor, and you might test it, and boy, that output looks like garbage, right? You can look at the signal, and it's not a good square wave. It may be noisy or dropouts or glitchy, something like that. And you might think, oh, well, I guess the cam sensor is bad. And you take the cam sensor out, put a new one in, and didn't fix the problem. And then you test it, and the same thing happens. Same thing happens. So when that happens, really the solution is to clean it, get all that gunk off of the magnets, and then you'll be able to do it that way. Oftentimes, they end up replacing the camshafts, the rockers, because at that point, the damage is already done internally anyways. So you usually have to end up replacing the camshaft to begin with. But you want to make sure it's clean. If it's not clean, it will cause some sort of a issue, drivability or otherwise. All right, so once I've gone through and tested my cam sensors, we want to make sure we have the good square waves or the analog pattern, right? It's a fairly cut and dry way the pattern's supposed to look. Oftentimes the manufacturers will publish a known good, and if you have a snap-on scan tool with guided component test in it, that has all known good patterns in there as well. But once I'm done with my testing, if I do need to replace my crank sensor, oftentimes, especially nowadays, we do have to have some sort of a relearn that needs to be done on these systems. So in this example, I pulled up a 14 Chevy Camaro with a V6, and this needs a crankshaft position system variation learn. So that's done with a scan tool, and it needs to be done if any of these things happen in a car. So an engine replacement, ECM or BCM replacement, crank balancer replacement, crankshaft removal and or replacement, a crankshaft position sensor disturbance or removal and or replacement. So if I even so much as disturb it, I need to do this. And then any engine repairs which disturb the crankshaft position sensor relationship. So this is to relearn basically the air gap and the variances in the metal and the materials there on that engine. So that is your variation there. So crankshaft position system variation learn. So how would I do that? We pull up the scan tool. Now we could go into engine and look for it, find it on the list there. If you have a tool with intelligent diagnostics or a Veris Edge with a current software, or on the intelligent diagnostic tools, it needs a current subscription or prepaid plan. Anyways, any of those occurrences, we have this quick link to service resets and relearns. So instead of having to go through, find it on the list, go to engine, find it that way, I can just have a quick link to it through here. So if we go into service resets and relearns, it's going to list all my relearns on the vehicle. Now, one thing I do want to note as well, on the latest software update that we did in the spring, maintenance was added to the top of the category. It makes it a lot easier. That's the common things you're going to do, right? Maintenance. Got to reset my oil light, or replace the brakes pads, and I need to retract the calipers or something of that nature. It's going to give you all that there. But below that, it's going to be categorized resets, relearns. So under the engine, we have a replace or relearn the crankshaft position sensor. So that's where we want to check that out. Notice it's by job. So I want to go in there, and then I'll just click on it, and then I'll see my crank position variation learn. If I click on that, it walks you through a few different steps. You have to rev the engine a few times, and then it will learn the crankshaft variation learn. So that's just on GM. On Ford, they have the misfire monitor neutral profile correction that they have there. If you were here at the very beginning, we showed a video on that. So many different vehicles, and those are just two examples, but many different manufacturers, many different vehicles require that we do a reset after replacing our cam and crank sensors. So we want to make sure that gets done as well. And service resets and relearns, a nice quick way to do that. All right, so let's go live on the tool. Tool should be up. There we go. All right, so now we're going to talk. Now we talked about cam sensors and crank sensors. They're going to work pretty much in the same way. They might just have a different signal pattern that they put out. So first off, how do I figure out what the signal pattern is? And then another common question we get asked too is, well, how would I do a cam and crank correlation on a car in case the timing belt jumps or a chain snaps or something of that nature? I want to be able to see that without having to disassemble the engine. Well, if I want a known good pattern and I have a snap-on scan tool with guided component tests, I can go into the guided component tests and it will show me a known good pattern right here. So if I go into engine in this case, by the way, guided component test, over 5 million available tests, goes back to 1981. Wealth of information in there. But if I want to check, say, a crank sensor, I'm going to the crank sensor on this car and I can go to my signature test. It's going to give me a known good value or a known good picture if it's a picture. So in this case, voltage should swing -7 to 7 volts. That is an analog voltage generator like we had at the very first thing we talked about. We back up here and go to the cam sensor. If I go to the cam sensor and do a signature test, that's going to show us not my signature. Good deal. Okay, so there we go. So we'll go in here and we'll look. It's going to tell us how it works. Cam position sensors are Hall element type, so it's a Hall effect sensor, so we know it should be a digital square wave, which read off of 3 slots on the end of each intake cam. All right, so be able to test it that way, and then it's going to tell us where to hook up, right? So we should be able to see it, yellow to power in this case, black to ground, or yellow to cam signal, black to ground, okay? So I can find known goods in the tool. Also, oops, shouldn't have gotten rid of the car. There we go. Also, manufacturers do publish known good patterns in there as well. So if I load this vehicle into my repair information, in this case, we're using ShopKey. It's going to load my vehicle. And it's going to pull up all the information I need, right? So we have our landing page here. It looks based on over 103,000 real world repairs. I'm going to pull up the crank position sensor. And when I do that on this car, it's going to ask me if it's not automatic or a standard. And if we go into like component operation, for example, it's going to tell us how it operates, right? So there's my cutaway, it tells us how it works. And there is my known good pattern for this vehicle, right? So in this case, we have multiple teeth around there. And then here's what the pattern should look like. So on this vehicle, we have an analog type signal generator on the crankshaft. It's going to have one gap here, see a single gap there, and then a double gap right there. So that's what my signal should look like. Gives me a known good pattern there. Now, if I go to, let's see, I want to go to, that was diagrams. Go to remove and replace. On this, we have an inspection. So it actually tells us to hook up with a scope and inspect it. And we can see our crank sensor there as well. It's going to give us the same type of pattern. It's going to say, here's what it's supposed to look like on a scope. There's my known good there. Okay. And then I think it's under specifications. Let's see. There we go. Specifications. Under specifications for a crank sensor on this vehicle, we also have our known good cam crank correlation pattern. So it's got 2 cam sensors. It's a horizontally opposed engine. So there's what my crank sensor is supposed to look like, and there's what my 2 camshaft sensors are supposed to look like. And there's how they're supposed to line up on a known good vehicle. So some manufacturers do publish known good cam crank correlation information. So that's pretty handy. If you need that, you can look up crank sensor. Oftentimes it's going to be under there. Depends on how the manufacturer lists it. Or you could look up a cam or crank sensor code. Oftentimes manufacturers will have it in there as well. So let's analyze a cam crank correlation recording off this car. Okay, so here's my cam crank correlation pattern that I have on this vehicle. Crank sensor on the top, 1 cam sensor, 2nd cam sensor. And then so we know what cylinders where. We actually tapped into a fuel injector. What you want to do in order to keep it centered on the screen, or keep it straight where exactly it is on your screen there. You want to do something that fires one time in a firing order. So it could be a coil. In this case, the injector was nice and easy on top of the engine, so we hooked up to the injector there. So usually cylinder 1 is best, so we can keep our firing order in mind too. So 1, 3, 4, 2 is the firing order on this vehicle. So if we see we have our crank sensor, and it's that analog signal generator type, goes up to about 13, 14 volts, negative 13, 14 volts. So it's a swinging on both sides of 0. I have that single gap and that double gap we were talking about earlier. And then on my cam sensors, they're Hall effect switches. So we have this one here, that's 5 volts, and this one here, it's 5 volts. And you can see that my blips line up. So on this cylinder, I have a single gap, a blip, a blip. On this one, I have a double gap, no blip, and a blip. Single gap, 1 blip, no blip, and then double gap, blip, blip. So between the combinations of these 3 things, we'll send a signal to the computer to tell what cylinder is active at the time. Right, so I can see that, and this also matches that known good cam crank correlation we looked at a little bit earlier. Now, you may be wondering, well, if this is good, how do I know when it's off? Right, so it depends on where we're looking. So let me go and turn my cursors on here. So we can talk about some math. I know math is super fun, but we need to use math sometimes when it comes to diagnosing a vehicle. All right, so if I put one cursor here on that single, and we notice how my injector is firing there, so we know that's that cylinder. And then we go the next time that injector fires again and put it on the same spot on my crank signal. That is 1, 2 times around on that crankshaft, because we have a 720-degree crank rotation for every time we go through the firing order, right? So crank spins twice, cam spins once. So if I were to measure this and see how long does this take to turn one time, it's 136.88 milliseconds, right? So we know it's 136 milliseconds, let's say. We'll just round it down to 136. So I take that 136 divided by 4. That's going to tell me how long one of my strokes is out of the 4-stroke engine, right? So we take how long it takes to do all 4 strokes divided by 4 gives us our how many per stroke. So 34 milliseconds. So let me take this and bring it over here, and I bet you we're going to be pretty darn close to 34 milliseconds right there. 34.12. I can't get much closer than that just by eyeballing it. All right, and then if I go to the next one on my crank, it should be what, 68, right? 68.24. Right on. All right, now let's go to the next one. It should be 102, 102.49. So each of my strokes is going to be at that difference apart. Right, so we have that right there. So 34, 33.99, close enough, right? So we have those measurements. So that can tell us our different strokes. We can also see how far off is my cam sensor. So if I leave the crank sensor there, and then I put the second cursor where my cam sensor starts, I will get 2.36 milliseconds from there to there. I got to back up one. So 2.36 milliseconds, we'll remember that. So let me go back here. So we said 136 milliseconds it takes for 720 degrees, right? So we'll go there, 136 divided by 720 degrees, 1.19 milliseconds per degree is what that will add up to. So 0.19 milliseconds per degree. So if we remember that, and we put that right there, and I take my measurement, 2.36 divided by 0.19 should be, nope, I'm sorry, times 12.9. See, I got my math wrong. It's 2.36 times 0.19. 4 degrees. No, yes, no, yes. 236. 236 divided by 0.19. There we go. 12 degrees. 12 degrees. That was my math. 12 degrees. So it's about 12 degrees between there and there. So if I had a jump timing belt or a stretch chain or something like that, if my cam was retarded, it would be to the right. And if my cam was advanced, it would be to the left based on the crank sensor. Right. So if the crank sensor is really more stationary. So we look at the cam sensors when that happens. So retarded be to the right, advanced to be to the left. So if they were off and these didn't line up, then I'd know I probably had, if it was a belt, the belt jumped, or maybe it wasn't installed correctly. And then also I can look and see if my chain stretched. Now, variable valve timing can throw a wrench into it. We need to disable the variable valve timing system sometimes when we make these measurements. But overall, you'd be able to see how do they line up and how many degrees are they separate. So that is all we have today for cam and crank sensors. So let's talk about what we're going to talk about next week. Because remember, as we said, all new classes we're starting today. So next week, we're going to get into the cooling system electronics. So coolant temp sensor, right? That seems fairly straightforward. But how about you ever current ramp a cooling fan motor? Right? That's something not a lot of people think about, to see how that coolant fan is operating, because it works on the same principle as current ramping any other electric motor out there. So we'll go through that. A couple other control systems, electric water pumps, things of that nature. So we'll talk all about the different electronics in the cooling system next week. Same time, same place, 6 and 9 Eastern, just as we're doing right now. If you want to go to snapon.com/OT, you can register for Zoom. So I see a couple people asked on YouTube how to register for Zoom. So to register for Zoom, you go to snapon.com/OT, and then you can then register and join us on Zoom if you want to do it that way. Or you can watch us live on YouTube, because we'll do the first session at 6 p.m. on YouTube. So on youtube.com/Snap-on Diagnostics, make sure you subscribe, give the video a like, and make sure you ring that little bell, the notification bell next to the subscribe button, so you get a notification every time we go live or post new content. Also, all of our previous episodes of our live streams are up there. So we have 22 different episodes, anything from ADOS to data bus testing to thermal imagers, and all of our component testing series is up there as well. So we have a multitude of different classes that you can take. And these, of course, will be recorded live to YouTube as well. So once again, youtube.com/Snap-on Diagnostics for that. Let's get to some questions. I see one just popped up on Zoom, and I will go talk about my buddy Al first, though. So my buddy Al, though, also does training. So we do training 4 nights a week here at Snap-on Diagnostics. So you're never for a lack of training, that's for sure. So same time, same place, 5 and 8 Central, 6 and 9 Eastern. Go to snapon.com/OT to register for Al's classes. So you'll see my face on the left side of the screen, Al's face on the right-hand side of the screen. Whatever class you want to register for, those are the one you go to. So Mondays, Al teaches Apollo. So here's how to set up your tool. Here's how the tool works, right? We're going to go all the way through setting up your Wi-Fi, through let's set up your free Snap-on Cloud account, through walkthrough of intelligent diagnostics. How does that help us diagnose a car faster? And then on Wednesdays is Zeus, and Thursdays is Triton. So the Apollo class on Monday is about an hour long with all that. Wednesdays and Thursdays, it's the same thing, just on a different tool for the first part. But then after a short break, he takes about another hour, goes through guided component tests, scope, meters, all the different scope and meter functions of the tool through that second half. So those classes are closer to 2 hours. Very, very thorough walkthrough on how those tools work. So that is only on Zoom. So make sure you register for those classes if you're interested as well. So let me look at Q&A. James is asking on Zoom, do I do airbags? Need to know how to get into the airbag module. So as far as scanner, we could definitely get into the airbag module and do, if I have to put a VIN in or any diagnostics that way, maybe some data coming out of the airbag module. Not a lot of functional tests really in there on the airbag module, because really what's the only thing we're going to be able to do? Probably blow it up. But, for yaw rate sensor recalibration, things of that nature, I think that's what you're asking is, does the scan tool do airbags? It certainly does. Across the board there, does quite a bit of things with that. So hopefully that answered your question there, James. Let's look on YouTube. So a couple people, as I said, were asking how to get into Zoom. So once again, if you go to snapon.com/OT, and you'll be able to register for any future Zoom classes if you want to do it that way. Let's see. Hey, Gracita, you were late, but that's okay. You can always rewind. You can always watch the recording. Naveed, yep. Send me an email, and I'll be able to we'll be able to talk with that. So Jason.Gabrenas, Gabrenas at snapon.com, and I'll be able to get your information that you need there, Naveed. Let's see. Adam McConnell asks, what's the cost of ShopKey? So I can tell you the retail price, the list price that it would be for anybody. There are discounts available, and there's always promotions going on too. But until the end of the month, it's actually going up $5 too. But until the end of the month, this month in August, $169 a month. That's going to be $174 a month starting September 1st. And then, of course, any discounts would bring that lower as well. Definitely talk to your Snap-on franchisee and have them get their diagnostic rep to talk to you, and they can absolutely help you out there, Adam. So thanks for that question. All right, looks like we are in good shape here, folks. We've answered all the questions. Thank you very much for sticking with me through those technical difficulties there as well. I'd like to thank you for taking time out of your day and coming and joining me, and hopefully learning a little bit more about how do cam and crank sensors work, how do I test them, what are they supposed to look like, and going through that cam crank correlation as well. So definitely thank you very much for joining me, taking time out of your day. It's Tuesday. Hopefully enjoy the rest of your week. Enjoy your weekend, and hopefully we'll see you next week for coolant temperature or coolant electronics testing next week. So with that, thank you very much and take care.